Okay, so I'm going to go through this solution to the in-class assessment that you guys did today, or whatever day it is you're going to watch this. So this question says there is a playground merry-go-round that is essentially a 100 kilogram disc. So that gives you an indication of the kind of inertia that it might have. It is a disc of 100 kilograms, and it's 2 meters in diameter. So across is 2 meters. That means the radius is 1 meter. The spinning axis is well lubricated, so there's no friction. The bars at the top are hollow and weigh almost nothing compared to the weight of the disc. You apply a constant force to one of the bars, tangent to the diameter, for 2 seconds. So what happens is it doesn't actually tell you which direction that force is, so I went ahead and drew this blue arrow on there that indicates, in class I added the directional information on the force. For 2 seconds, after which the merry-go-round is spinning at a rate of 1 rotation every 4 seconds. So what's going on here is it's at rest, and then you push it for 2 seconds, 1, 2, and you get it going at a constant rotation of 1 rotation every 4 seconds. So that's how that's working. So the question is, what's the value of the angular speed in radians per second? And is this positive or negative to the angular velocity? So what we want to do is we want to know, well, speed, angular speed, is the change in the angle divided by change in time. And what we know about this is it went 1 rotation in 4 seconds. So that means it went 1 full way around. So that's 360 degrees, or it's also 2 pi radians. So it's 2 pi radians in 4 seconds. And that's just what we're going to do, and then we just calculate that out, and it's actually 0.5 times pi, which is 1.57 radians per second. So we'll go on to the next question. Oh no, and also the direction is positive because that's a counterclockwise direction when we're talking about velocity, angular velocity. So the next question is, what's the angular acceleration created by the turning force? So if you remember, it started at rest, and then it went up to whatever the final velocity was, which we calculated here, 1.75 radians per second. So it was at 0 initially, and then it went to 1.57 radians per second. And we did this in 2 seconds. Remember here it says we pushed it for 2 seconds. So what we'll do is we'll look at what's the change in the angular velocity with the change in time. We're going to take the final angular velocity minus the initial, that's change, over the time. So we're going to get 1.57 minus 0 because it began at rest, ended at 1.57 radians, and it took 2 seconds. So that's 0.27 radians per second squared. That is the angular velocity. And because of the right-hand rule, we know that the direction is positive or upward. The next question is, what's the approximate rotational moment of inertia of the merry-go-round? Okay, so this is not really about this particular problem, it's about the merry-go-round in general. And what happens is the inertia of a disk, we have to look this up, is equal to 1/2 the mass of the disk times the radius squared. That's just, we can look that up in the table. We're going to plug and chug this, 1/2 100 kilograms, if that's what it said in the initial problem, and it's 2 meters across, so we'll use 1 meter as the radius squared. That's 50 kilograms meter squared. That's the units for inertia. So we have that value I. The next thing is, what's the value of torque applied to the merry-go-round? So torque is, there's 2 different ways we can calculate torque. One is the force times this moment of inertia, or that, not moment, the torque, force times the distance between the force and the center, the rotating point, or D, or it is an inertia times acceleration. So we're going to use this equation because we have inertia and we have acceleration in the previous one. And we want to know, of the merry-go-round, as it's going around, what is the torque? So we calculated I already, and we calculated acceleration already, 50 and 0.79. So that means we can just get the torque, which is 39.5 newton meters. The next question says, what's the actual force that's applied? So you have this force, you don't know what it is yet. but it makes up the torque. And so we know torque is also equal to the force times the distance between the force and the center of rotation. So we can just take 50, the torque, which we already know because we calculated earlier, is 39.5. That's that value. And we'll put that value equal to force times distance. And we can solve for F, and then F is actually equal to the torque, kind of accidentally. It's 39.5 newtons. The force is equal to the torque, 39.5 newtons. I hope that helps.